Okay, section 6.3, maximum and minimum problems. And you might be saying to yourself, well, we've already done maximum and minimum problems. Yes, but we have not done them with multiple variables, and it does lead into a slightly different type of math here. And just to make sure you understand, 6.4, there will not be a video. It's just the notes. So go ahead and look at the notes, and because there's really no examples on that one. So look at the notes, and hopefully you'll be okay with that. All right, 6.3. Our objectives: find relative extrema of function of two variables. The vocabulary: we've got contour plot, saddle point, and the D-test. So let's go ahead and start looking. So these were done with Wolfram Alpha. We're going to consider the graphs of some two variable functions. We're also going to look at the contour plot associated with each one of those graphs. And this contour plot is a top-down map. In other words, if you were looking directly above the graph, think of it as if you were looking at a mountain. If you look at a mountain from the side, you can clearly see the height of the mountain. But if you were to look at a mountain straight down from space, all you would see is basically a flat two-dimensional figure. And I'll kind of point out what I mean by that. So the contour map represents, the different colors represent the height of the function. The darker the color, the lower the point. A lot of times contour maps, which is like the map on the right-hand side of this first example, actually put numbers which represent the general height of the function, and I'm going to kind of add that in there for you. But what we can do is we can use contour map plots to examine features of a graph that might be difficult actually to see in 3D. So our first example, example 1, the function, and both of these graphs, by the way, are the same function. One of it's just looking at the three-dimensional figure, and the other one is looking straight down at it from the top. So obviously what you have here is this is the three-dimensional figure. And then the contour map, which is this one right here, is looking at the three-dimensional figure straight down on it, just like that. You're looking right as if you were right above it. So it's f of xy equals x squared plus xy plus 2y squared minus 7x. The graph has the shape of an oval bowl. It's hard to see it from the one in 3D, but it's a little bit easier to see the one here that's the contour map. You can almost kind of see the oval shape of it. And then if you can imagine this centerpiece right here, this piece right in here, as the darkest part of the map. I'm going to erase that green, but the darkest part of the map, it's the deepest part of the bowl. And then the lighter it goes towards the outside, the higher it becomes. So it's more like going up towards the side of the bowl. Okay. What it appears, and you can kind of see that one a little bit better from this one right here, it appears that at the point 0.05, that seems to decrease to what seems to be some kind of a minimum. So let's check that out. Here's x is 0 right here. Here's y is 5 right here. So if we kind of go out this way and then out this way, you can kind of see how that might actually equate to a minimum. It looks like it's probably the lowest part of the graph in 3 dimensions. You can see it a little bit more, well, actually, yeah, you can see it a little bit more clearly. I think this graph might be mislabeled. I think that the contour map graph actually might be mislabeled a little bit because it's supposed to be at the point 0.05. If I go to 0.5 with x being 0 and y being 5, that's going to be someplace right up here. That's not really where we're supposed to be. I think maybe that the graph is actually mislabeled, because if I go to the point 0.5 where y is 0 and x is 5, that looks much better. So I think that the graph is mislabeled. That's a mistake. Just know that it's supposed to be at x is 0, y is 5, or maybe it's supposed to be at 5, 0. Harder to tell if that was just a mistake, or maybe it was a mistake in the typing. But you can clearly see how someplace in that dark region right there would be your minimum, because it's the darkest place on the graph. Again, this is just really developing the idea behind what's going to happen here. If we look at example 2, Example 2 is a little bit more interesting. If you look at the three-dimensional graph, that's kind of an interesting looking shape there. Looks like maybe you're talking about, we've cut off part of the side of a hill or a mountain or something like that, and we're looking at how it curves and, it kind of goes down, down the slopes or whatever. It's f of xy equals xy minus x cubed minus y squared. You would not know that this is what that looks like without actually graphing it. The one on the right-hand side is the contour map. I'm actually going to focus more on the three-dimensional map here, but we are going to take just a really quick look at the contour map. The three-dimensional map, if you look at that one, you can kind of look at it and say, okay, there looks like there's a relative maximum point at 1, 1. So here's x equals 1. Out here is y equals 1. If you were to kind of triangulate that, go this way, right there, looks like that would probably be like a relative maximum. It looks like it's kind of like the top of a little hill right there, right? At least I think it does. And then it looks like there might be a little bit of a dip near the maximum. So like down here, looks like it kind of comes down and dips down a little bit from both sides. So that looks like that could be a relative minimum. It's a little bit less clear from that. Now let's go to the contour map real quick. Just to show that, okay, the lightest parts of the entire map should be the highest, which looks like it's that little section right there, which definitely looks like, it could be, maybe there's a little dip there or something. I'm sorry, not the highest parts. No, I was right first time. The highest parts are the lightest parts. It's a little bit tougher to tell if you ask me from the contour map here, because the darker parts are going in this direction, so it definitely looks like it's going down. But this doesn't look like it's actually at that point. This looks like it's closer to like 0.250. And maybe that's really what this piece is right over here, 0.250. It's really kind of hard to tell because we're looking at these things from different vantage points. But you can definitely see how right around here, right around there, something like that is going to be where you've got the highest point. What I can tell you, however, is that there's going to be an easy way, well, not easy way, but there's going to be an algebraic way to find this information. All right, let's go to example 3, because example 3 is probably one of the more interesting ones. If you look at the figure on the left, this is actually called a hyperbolic paraboloid. It is a very, very common shape, and as a matter of fact, you might look at that and think, oh, that kind of looks like a Pringles potato chip. It's exactly what it is. A Pringles potato chip is actually in the shape of what you see here, a hyperbolic paraboloid. The edges are a little bit more rounded, instead of cornered, but that's exactly what it is. But the interesting thing about this x squared minus y squared graph is right here at 0, 0, there is a point of interest. It looks like you could have a relative maximum there. And if I look at it from this direction, in the direction of x right here, and then it kind of goes back down around the other side, which is hard to see, that's definitely a relative maximum. But the point also looks like it could be a relative minimum if I start up here and slope it down here and then come back up. It could also be a relative minimum. When you have such a point where you have both a relative maximum and a relative minimum at exactly the same point, it is what is called a saddle point. And if you look at the shape of that thing, it kind of looks like the saddle that you might throw on a horse. So that's probably why they call it a saddle point. All right, so we can actually, again, find these points of interest that we estimated in the graphs above. We have 2 tests for relative max and mins in one variable. Now this is going all the way back. We did the first derivative test, which was finding the derivative, setting it equal to 0, finding the critical values, and then testing whether it was increasing to decreasing or decreasing to increasing, and that would tell us whether we had a relative max or min. We also had the second derivative test, which was taking the derivative of the first derivative, so we had the concavity. If it was something which was concave up at a critical point, then we had a minimum. If it was concave down at a critical point, then we had a maximum. Question is there such a test for 2 variable functions? Well, I've already answered that for you. Yes, there is. So let's go ahead and take a look at that. It is called the Dtest. And the reason it's called the Dtest is because what we're actually finding is what's called a determinant. If you've taken some other classes, you may have seen that somewhere. but we're not going to get heavily into that. It's actually something which is very highly used in linear algebra, which is a higher level math course. But that's what the D-test stands for. You just have to know it's called the D-test. So what you do in order to find whether something has a relative max or min is follow these steps. You're going to find the first partials. You're going to find all three of the second partials. Notice I said all three of the second partials because technically, if you remember what I said in the last section, this one is exactly the same as fyx. fxy and fyx are the same. So you don't really need to find it twice. It's going to be exactly the same thing. You're going to solve the system of equations by setting f of x, partial of x with respect, partial of x equal to 0 and the partial of y equal to 0. And then you're going to let the solutions to that be the point. And that point is going to be your critical value. So that is going to be your critical value. And then you're going to evaluate this d at the critical value. And what d is, it's the second partial with respect to x times the second partial with respect to y minus the partial of f of xy squared. So times itself, basically. And then what you're going to find is that you're going to have a maximum if the d part is greater than 0. So if what we get here is greater than 0, and f of x is less than 0. So it's two criteria. Then you're going to have a relative minimum if, once again, the d part is greater than 0, but this time f of xx is greater than 0 instead of less than 0. That would give you a minimum. Basically, this part right here, these two things, are like the concavity part. So if you have a critical value and it's concave down, which would be the top one, part A, then it would be a max. If you have a critical value and it's concave up, which would be part B, then you have a min. If neither a maximum nor a minimum is at AB, then D is going to be less than 0. In that case, what you're going to have is a saddle point. The nice thing about if you get D less than 0, you're done. You don't have to do any other checks. It's just one thing. If D is less than 0, so if this piece right here is less than 0, you're done. It's a saddle point. If D equals 0, the test is not applicable. We probably should not see that case in anything that we are doing. All right, these problems can take some time, so you need to be very careful and very patient with these. So let's see what we've got. We'll take some time going through number 1. In order to find the critical values, the first thing you do is you need to find fx and you need to find fy. So fx is the partial derivative with respect to x. So we'll go through the pieces. The first part is going to be 2x. The second part is going to be y, because the derivative of x is 1. The next part, 2y squared and -7, those have nothing to do with x. They're gone. They're done. So we'll take that and we'll set that equal to 0. We'll come back to that in a second. In fy, we need to take the partial with respect to y. So when I take the derivative of x squared, nothing. When I take the derivative of xy, the derivative of y is 1, so that just leaves the x. When I take the derivative of 2y squared, I get 4y. And then when I take the derivative of -7, that's 0, that's done. So we need to set that equal to 0. Now there are multiple ways that we can solve this system of equations, because what I have now is I have 2x plus y equals 0, and I have x plus 4y equals 0. What I can do is I can take and I can substitute for one of these. In other words, I'm going to solve the first one for y, so just subtract 2x on both sides. And then what I can do is I can take that minus 2x and I can plug that in for y right there, and now I'm going to be able to solve my system of equations. System of equations meaning 2 or more equations. So let's go ahead and do that. So I'm going to get x plus 4 times -2x equals 0. So in this case, we're going to get x plus -8x, which is -7x, equals 0. Dividing both sides by -7, you get that x equals 0. And if x equals 0, we're going to plug that back into the equation over here. Use a different color. And then we're going to get that y equals -2 times 0, which is also 0. Now, in this case, we could have done this a completely other way to figure it out, but this is probably the easiest. Okay, so we've got our critical value. Our critical value is going to be at the point 0, 0. That's our critical point right there, 0, 0. So now what we have to do is we have to test that. Well, we still need the second derivatives. So let's go ahead and find those. I need fxx, I need fyy, and I need fxy. So let's find those. Fxx is the derivative of f of x with respect to x. That's 2. Fyy is the derivative of fy with respect to y. That's 4. Fxy is the derivative of fx with respect to y, which is going to be 1. You could do the same thing. You could do fyx. You're also going to get 1. It won't make any difference. So in our D says we're going to take fxx minus, sorry, not minus, times fyy minus fxy squared. And technically what we're supposed to do is we're supposed to plug in our critical point, but there's no variables in our fxx, fyy, and fxy. That will not always be the case. It just happened to be that they all worked out to be constants here. There's no variables in this case, so I really just have to figure out the D part. So let's go ahead and do that. So I'm going to have fxx, which is 2, times fyy, which is 4, minus fxy, which is 1, squared. So we get 2 times 4, which is 8, minus 1 is 7. 7 is a number which is greater than 0, so that means we're going to have a max or a min. So we're going to have a max or min, and we need to figure out what the sign of fxx is. Fxx is 2, so that's greater than 0. So because I have a critical value at 0, 0, and the second derivative is greater than 0, because the D value is greater than 0, and the second derivative of xx is greater than 0, that means it's concave up, which means that this is a min. So we have a min at the point 0, 0. And that's what we have to do. All right, let's do a couple more examples. I think we've got one more regular example and then a word problem example. So let's do the process all over again. We need to find fx, and we need to find fy to start. So the derivative with respect to x is going to be y minus 3x squared. The derivative with respect to y is going to be x minus 2y. We set both of these equal to 0, and we solve this system of equations. So I'm going to, once again, I'm going to go ahead and solve the first one. I'm going to solve it for y, and I'm solving it for y because it's the easiest variable to solve for. So we'll add, add 3x squared, go away. Okay, maybe that box will eventually go away. I'm going to take the 3x squared, I'm going to plug it into the y and the other side, so we're going to get that x minus 2 times 3x squared equals 0. So that's going to give me x minus 6x squared equals 0. I can factor an x out of that, and we get 1 minus 6x equals 0. So here I'm actually going to have two different critical values. I'm going to get x equals 0, and in the second one, I'm going to get x equals 1/6. Which means I'm probably going to get two different y values. So I'm going to have two critical points in this case. So I'm going to take the 0, and I'm going to plug it in for x. So we're going to get, if x is 0, we get that y is plugging 0 into y equals 3x squared is also going to give me 0. So my first critical point is 0, 0. The second one is going to be if x is 1/6. So then y is going to equal, I'll write this one out, 3 times 1/6 squared. Be nice if my 6's look like a 6. we go. And that one's going to be a little bit messier. It's going to be the 0.16, comma. Let's see, 1/6 squared is going to be 1 over 36, times 3 is 3 over 36, but that reduces to 1 over 12, so 1/6, 1/12. Both of these are my critical points. So we've got 2 critical points to check now. So we are going to need the second derivatives. So let's go ahead and find those. fxx in this case is going to be negative 6x. See, that one has a variable in it this time. Fyy is going to be negative 2, no variable in that one. And then fxy is just going to be 1. But we are going to have something to plug in. So when we do our D chart this time, I've got to do D for both points, 0, 0, and 1/6, comma, 1/12. All right, so let's go ahead and work this out. So we're going to have fxx times fyy. But fxx, once again, is negative 6x. We have to plug the 0 and the 1/6 in there to get a value. Excuse me. So fxx is going to be, for 0, 0 is going to be 0 times fyy, which is 2, minus fxy squared. That's going to be 0 times 2, which is 0, minus 1, so that's actually minus 1. That's less than 0. That's automatically a saddle point. So we have a saddle point at 0, 0. And then if I do 1/6, that's going to be negative 6 times 1/6. And then we still have to do times negative 2. Whoops, I actually forgot my negative in the top one. Didn't matter, but I did forget it. Times negative 2, and then minus 1 squared. So let's see, negative 6 times 1/6 is going to be negative 1, times negative 2 is positive 2, minus 1 is 1, and that's greater than 0. So we do have a maximum in there. We just have to check the sign of fxx. Well, fxx, in this case, at 1/6 is negative. And because it's negative, that means it's concave down, which means that we have a maximum, a relative maximum at 1/6, 1/12. And what I would strongly suggest doing, because we're done with that one, what I would strongly suggest doing in this case is plugging that function into Wolfram Alpha or CalcPlot 3D and just look at it at 0, 0 and 1/6, 1/12 just to see whether you can actually tell that there's a saddle point at 0, 0 and that there's a relative maximum at 1/6, 1/12. You're probably going to have to zoom way in because those numbers are really small, but that would be a good idea. Okay. One more example. Example 3. Fly Straight Incorporated produces 2 kinds of golf balls, one kind that sells for $3 and one that sells for $2. The total revenue in thousands of dollars from the sale of X thousand balls at $3 each and Y thousand at $2 each is given by R of XY equals 3X plus 2Y. Okay, there's a lot of stuff going on there, but basically they've given you the revenue function. The company determines the total cost of producing these same items is what you see below. I'm not going to read that whole thing there. How many balls of each type must be produced to maximize the profit? Produced and sold, excuse me, to maximize the profit. So the first thing we need is we need the profit function. By the way, this should say C of XY, not just X. C of XY. So we need revenue minus cost. Profit of XY is the revenue function, 3X plus 2Y minus the cost function. And again, put the cost function in parentheses just to make sure you don't lose it. Lose that minus sign because it's going to have to be distributed throughout. This is a long one. So let's simplify the profit. So let's see, do I have any other x's? Yes, 3x minus the minus 9y. So I'm sorry, 9x, 3x minus 9x is going to be plus. So that gives us 12x. 2y right here minus 6y is going to be minus 4y. And then we just need to distribute the negative sign to everything else that we didn't just use there. So let's see, what did we use there? We used the 3x, the 2y, the 6y, and negative 9x. Okay, so we just need to make everything else the opposite sign. So we're going to get minus 2x squared plus 2xy, that is a y, believe it or not, minus y squared minus 7. All right, now after all that, we can start doing the calculus. Let's take partial derivatives because we are trying to maximize this profit. So we're looking for a place where we have a maximum. So we'll take the partial with respect to x, which is going to be 12. The 4y part is nothing, minus 4x plus 2y. Okay, we're going to have to set that equal to 0 and solve it. Now let's do the y part. Partial with respect to y is going to be, the 12x part is nothing, so minus 4. The negative 2x squared is nothing, then we get plus 2x, and then minus 2y, and we will have to set that equal to 0 and solve it. Okay, the nice thing is here, and hopefully you'll be able to follow this, there's going to be a bit of a shortcut, and if this is not something that you noticed, that's okay. There's other ways to do this. I'm going to add 2y on the second equation on both sides. So we're going to get negative 4 plus 2x equals 2y. And you might think, okay, why specifically did I see to do that? Well, what I see is this. I see that 2y is there, and I also see a 2y is there. So I'm going to take all of this negative 4 plus 2x, and I'm going to plug it in for 2y. Not for y, for 2y, because that's what it is. So I'm going to get 12 minus 4x plus negative 4 plus 2x equals 0. Okay, I hope you followed that. If not, you can solve the equation for y itself, do a substitution in for y, and then you're going to end up at the same place, hopefully. So now let's simplify. I've got 12 minus 4, which is 8, minus 4x plus 2x is minus 2x equals 0. Solving this for x, we get that 8 equals 2x. Dividing both sides by 2, we get that x equals 4. So now I'm going to take that 4, and I'm going to go ahead and plug that in for x right there so we can solve for y. So we're going to get negative 4 plus 2 times 4 equals 2y. So negative 4 plus 8 is 4 equals 2y. Dividing by 2, y equals 2. And now we have our critical value at 4, 2. That's our critical point. We do have to double check that this is a maximum and not a minimum. So let's go ahead and use our d-test. Now we have to do all the other partials. So let's go ahead, let's go ahead and do that. So we're going to do, wow, sorry about that, pxx, which in this case is going to be negative 4. We're going to do pyy, which in this case is negative 2. And we're going to do pxy, which is going to be 2. Nice thing about that is there's no variables. So at our critical value, all we need to do is the d-test. And d is pxx times pyy minus pxy squared. So negative 4 times negative 2 is 8, minus 4 is 4. That is a number which is greater than 0, so it's definitely a critical value. Let's make sure that this is now a max. So we have to check the sign. Pxx is less than 0, which means it's concave down. So this is indeed a maximum at the point 4, 2. Now, because it's a word problem, let's just double check that we're actually answering the question. How many balls of each type must be produced to sell the maximum, to give the maximum profit? So it looks like the x is Oh, it just says 2 kinds of golf balls. So we're going to have to, if it gave us names, we'd have to go back to the names. We have to sell 4 of the X type and 2 of the Y type. And that's it. A little bit over 30 minutes for this video, but that is the last video for the course. Good luck, and it's been a pleasure.